Hi, everybody. I hope you hear me correctly. If not, and if yes, you can say me if everything is okay. So I think everything is good. So we can start. So thank you for joining us today. My name is Hélène. I am a geophysicist specialized in geostatistics. Today, I want to introduce you the use of multi-point statistics simulations approach to improve your models. This technique can be applied to model spatial or temporal variability when dense datasets are available to train the algorithm. During this webinar, we will see theory and practice of multi-point statistics techniques with our software Isatis.neo. We will also have the chance to welcome Philippe Renard and Julien Strober, experts in the multi-point statistics simulation and at the origin of the development of this new technology. Later, Philippe presents us some practical example of the use of MPS in hydrogeology, mining, and other domains. We will be together for about half an hour. Please note that I have turned off your microphone to ensure better quality of communication. However, you will be able to send me your messages through the question zone, which is located in the GoToWebinar control panel. Please feel free to ask your question at any time. I will answer them at the end of the webinar with Philippe. And a video of this webinar will be sent to each registrant after this webinar. So if you have some questions later, you can also come back to us. So why we want to use MPS and what they bring to you. Multi-point statistics is a simulation technique allowing to generate images that reproduce the spatial features present in a training image. Among the techniques used to simulate categorical variables, multi-point statistics is becoming very popular because it allows the user to provide an explicit conceptual model via a training image. MPS algorithm consists in sequentially filling a simulation grid such that patterns around the simulated values come from the training image. Following this principle, joint simulations of multiple variables can be handled, and complex heterogeneous fields can be generated. However, inconsistent patterns are often found in the result, and some spatial features can be difficult to reproduce. It is why we implement in Isatis.neo a new MPS algorithm based on a multi-resolution representation of the training image. So it is based on the direct sampling, and now I let Philippe present some examples.
Thank you, Hélène. Hello, everyone. So today, I will start by just showing some examples. I will not explain all the details on how it works. This will be explained later by Hélène, and she will make a demo to show you the basic principles. But the idea here is to just talk a little bit about the motivations. So the main idea of DeeSse, of the direct sampling technique, was to generate models that are more realistic than what we do usually with the more traditional geostatistics. And this, can I have the?
Yeah.
Is it working? Yes.
Yeah.
So there is just a little light. So the motivation of developing the direct sampling and using multiple point statistics principle, in fact, came mainly because we are doing hydrogeology. So we are modeling flow in the underground. And in my field, which is hydrogeology, and also in petroleum engineering, the connectivity of the hypermeability features underground is very important because it controls how the fluids flow. And when we started to work with these techniques, we made a nice little example that I will show you now to illustrate this idea and why is it important to reproduce the connectivity properly. So what you see on the left here is the satellite image of the Lena Delta in Siberia. And we used it, so it's just a photograph, but we used it as an analog of what could be present in the underground, and to check and test what are the performances of traditional geostatistic techniques when you have channelized bodies of possibly hypermobility material. So we took this image, we assumed that the blue colors here in this false color scheme represent the hypermobility zones, and the red are the low permeability. Green are somewhere in between. So based on this image, which is completely known explicitly everywhere, we can compute the histogram of all the values. We can compute the variograms in different directions, evaluate the anisotropy, and then you can use traditional geostatistics to model a random field that would have the proper histogram and the proper variogram or covariance. So this is what you get. When you compare just visually with the reference which is on the left, you see directly that you lose. So this is an unconditional simulation. Huh? There is no borehole data here. It's just a simulation that shares the same first order statistics than the image of the Lena Delta on the left. And so you see that the hypermobility zones, they are limited to some kind of elongated but limited size lenses of blue here everywhere. So if now we use MPS, using a continuous variable, because we can use continuous variable with the direct sampling, you get a simulation that looks like that. So that was a simulation that we did almost 10 years ago. It's not perfect, it's broken. Now the new simulations would be maybe better. But here the message that we wanted to pass is that you get some connectivity of the blue patterns here, because we are borrowing these statistics from the training image with multiple point statistics. And so the structures are very different between our direct sampling simulation and the multi-Gaussian one. And if we look at the statistics, so histograms on top here, you cannot distinguish these two simulations. If you look at the variograms, also in different directions, you also cannot distinguish these two simulations. And this is well known. This is something that Sébastien Strebel shown a long time ago. And what you also know in advance is that for flow simulation and transport, these two simulations will be very different. So here, if you impose on the left side a concentration of 1, and if you impose boundary conditions that makes a flow from left to right, and if you look at the concentration of this tracer in the direct sampling image, you will see that it will follow the channel and go through the medium, while in the multi-Gaussian medium, it cannot go far away because these lenses of hypermobility are somehow isolated, and so the flux is going much slower. So if we look at the breakthrough of this tracer on the other side of the medium, on the right side, you see that the breakthrough is arriving much faster in this image than in the multi-Gaussian one, and much slower in the multi-Gaussian. Also, that makes a lot of sense. So now the point is, what you have in the underground is always uncertain. So if you are interested in the uncertainty, if you are thinking about, for example, evaluating the risk related to a waste disposal that would be positioned somewhere on the left side of this domain, and you want to know when the contaminant may come out of this system on the right side, if you may pollute some drinking water supply, for example, if you make many realizations using multi-Gaussian geostatistics, you will have some fluctuations, but you will always have a behavior that will be limited because these high permeability zones would not be connected, and therefore the uncertainty would be highly underestimated. So having a broader range of geostatistical models is very important because it will allow us to better represent the uncertainty about the underground and be able to account for different kinds of connectivity structures. So the reason why we have this difference is rather obvious. Many of you know it already. If we compute the covariance or variogram on the images, they are the same for the cases that I have showed here, but the connectivity function, so the probability to have 2 points belonging to a high permeability zone at a certain distance from between 2 points, they will not be the same between the multi-Gaussian simulations that are in green here and the one that you have with the direct sampling here in that case. So that was our motivation to start developing all this algorithm, the direct sampling, Impala, and all this stuff. But now I will show you 4 little examples in different fields. What I have to say is DeeSse is now getting applied in many different fields. There are many publications that are done not only by us, but by other groups in the world. Yes, and sorry, there is a lag when I click. So the first example that I want to show you is one that we recently did, in Switzerland. So it's a case close to the city of Bern. You have this little map on the left side. The city of Bern is located here, and southeast of Bern there is an alluvial aquifer that is rather densely populated. It's kind of suburb area. You see a lot of houses, individual houses, and people are commuting between Bern and this area. So in this aquifer, they use the water for drinking supply, but also for heating all these houses. And there is a lot of geothermal heating. And what we wanted to do was to characterize the aquifer for geothermal exploitation, also for groundwater resources evaluation, but also because a part of this aquifer is used for gravel supply for building, for construction. So what we did was to conduct a geophysical campaign, and all the black lines that you see here are geophysical measurements that we collected using a towed electromagnetic device. And you see that we went in almost all the fields that we could, but there are places where we could not go. For example, here there is an airport, so you cannot go. There is all the city here, you cannot go. And so there are a lot of gaps in our data set. So here you see a vision of the data, and all this geophysical data has been inverted to get the resistivity logs as a function of depth. So these are in color values of resistivity that indicates the type of sediment that we have on the ground, but there are plenty of holes in this domain. We have also some boreholes. All the red dots are the boreholes, and some boreholes are in the places where we did the geophysics, some are in the city. And from the boreholes, we have another information, which is the clay content. So what we did was a geostatistical analysis of the relation between resistivity and clay content, and we used the DeeSse algorithm to interpolate both resistivity and clay content in 3D in the whole area. And here you see one example of this reconstructed resistivity map, but we have also the clay content map. So that's one example of how you could use DeeSse for this kind of applications. So here, the training data were directly the measurements collected in the field. So another more traditional use of MPS, this is the PhD thesis of Valentin Delalba. This is an aquifer in the southeastern part of France, close to Perpignan. So here you have a coastal aquifer, and here groundwater is heavily pumped for irrigation and for the population. And so there is a risk. We are just along the shore of the Mediterranean Sea. So there is a risk if we overpump to let seawater intrude the aquifer and then pollute the groundwater and the water for irrigation. So the BRGM in France, the French Geological Survey, is studying this aquifer in very much detail. And there, Valentin is modeling the system. So here we work with geologists from BRGM who have a concept of how the sedimentation was deposited in this environment. And they have a concept, sedimentological concept, where on the upper part of the catchment, you have some alluvial fans, and then you go through a succession of transition from braided system and then meandering systems in the more distal part. So here you see the kind of simulations that we could do. This is just an example in 2 dimensions, but it's a 3D problem. And with DeeSse, we could integrate some maps of paleo orientation of the channels in the area of the rivers, and also some trends. Here I don't show the map of the trend, but you see that the training image has a trend. It's not a stationary training image. It has a trend from the upper part of the catchment to the downstream, and we respect this trend because we have secondary variables that describe the trend in space. Okay, so that's a bit the traditional way of using MPS, where we model facies, but with trends and continuous variation of the angles. And now I'll show you a mining example. And this is an example that we have not done ourselves, but which was made by Jelena van der Riep from Anglo Gold Ashanti, so in South Africa. And what you see on the left here is one realization of a model of the facies, the rock. So in purple, you have the banded iron formations, and in green, the diorite. And so this is a conditional simulation. You have plenty of borehole in the area. And here you see a cross section through this system. You see all the boreholes and you see the facies along the borehole. And what is really nice in this example is that in this paper that they published, they used the orientation of the structure, the geological structure that they derived from the observation in the boreholes and in the tunnels everywhere, where they have the information about the folding and etc. They interpolated this orientation, and then they made a very simple training image with just a layered system with an alternation of diorite and banded iron formation. So just horizontal layers, but using the field of orientation, they get these very nice patterns, and they believe it's pretty close to what they have in mind for the geology of the area. And you see that it fits very well all the borehole data, and it fits also the structure, all the folds and complicated structure that they observe on the ground. And in the second stage, what has been done was to model the ore grade using the facies as a constraint to model the grades. And for that, the training image that they used was a part of the mine where they had a lot of data. And here it's more complicated. I think there are still some research to do on how to do that as best as possible. But for the geology, they were really happy with the results as far as I know. So last example, it's just to highlight that direct sampling works with continuous and categorical variables. You have seen examples of both. If it works with continuous variable, you can apply it for time series. So this is an example taken from the PhD thesis of Fabio Oriani a few years ago. And these are simulated rainfall patterns in Australia for the city of Darwin, so in the northern part of Australia, where you have a kind of tropical climate, and you see this simulation of rainfall. So here, the training image is the record of precipitations in the past, and from this training image, we are able to simulate rainfall patterns that are close to the true rainfall patterns. So how do we know that we are good? Because we compare the simulations with indirect statistics that are derived from the data here, but that are not imposed when we do the simulation. So for example, we can count for every month the wet days probability, and in red you see the reference, and the box plots show the results of our simulations, and they fit very well the data. Same thing for the maximum cumulated monthly rainfall by month. We follow properly the statistics, but this is not imposed in the simulation. So in the simulation, simply what we do is we give the training image, we have a few additional variables for the seasonality, and that works automatically. And what is very nice is that you don't have to play with parameters. You just give a training data set from Darwin, and you get the simulation for Darwin. If you apply the same, exactly the same, we don't change any parameter for Alice Spring or for Sydney, we also get excellent simulations with a very good comparison with the true statistics. So that is very handy, because you can simulate this and then use it maybe, for example, for studying the impact on water resources or whatever. So that's it for the examples. I will now let Hélène take over the presentation, and I thank you for your attention.
Thank you, Philippe. So I can continue, and I want to show you now all the different information and how MPS works with small details, but all the principal information. So here how it works. So here we have an illustration of the algorithm for the simulation of one cell. So we want to know which information we have here, for example, and in order to define this value, we need only 3 parameters. So the first thing, it is to check in the training image if all the different cells that we have are linked or have the same information in the patterns, and if we can put the value here or not. So like that, we compare all the different information that we have. So it is why we need to define the number of information, the number for the neighborhood, and it is the value that we define with the n. And after that, we have to check if we have the same value or not. If yes, we can copy paste the value on the simulation grid, and if not, we try with another cell. It is the case here. So here we check if we have the same value in the pattern distance, so the second parameters, and if yes, we copy paste the value in the simulation grid. And we do this research depending of the third parameter, so the fraction f, in all the different patterns of the training image. So with only these three parameters, we can compare the training image, and we can put the value in the simulation grid. So if we if we want to compare this method of simulation with another one, here we doesn't work. We don't work with a variogram. It's just a multi-point information. We scan the image and we want to reproduce these conditional statistics. So why we say that DeeSse, so the direct sampling, it is a revolutionary techniques for the multi-point statistic code. We can work, like Philippe said just previously, with a different simulation with continuous variable and also with the categorical information. And we can mix a continuous variable with a categorical one. We have also, so like that, we have the possibility to work with joint simulation of several variables, continuous with other continuous and categorical, or we can mix both of them. We work like that with multivariate training image, and it is also possible to work with training image not stationary. And we have also the possibility, we don't need to compute conditional probability on facies. So this new techniques from direct sampling is very flexible, and we have also less memory requirement because all the different information are parallelized and several nodes are simulated simultaneously. We have also a reproducibility like that, same result as those provided by serial code. In this new techniques, the direct sampling handles a wide variety of constraints. So we can work, like I said, with categorical or continuous variable. We can use one or several variables together. We can also conditioning with hard data, conditioning with connectivity data. We can work with the non-stationarity, so we can use rotation or homotachy. We can use some proportion, and in this case, we can work globally or locally to describe our training image and what we want to obtain in the simulation grid. We can use trend variables, so correlated variables known on the training image and on the simulation grid. We can work with multiple scale simulation. So in this case, we work with that we call Gaussian pyramids. And we can use, like in the first example of Philippe, incomplete training image. So it is something with a large flexibility, with a lot of options, and like that we can work very easily. All grid, so simulation grids, training image are also in grid or defined on 2D or on 3D regular grids. So now I want to show you in details some of this option. So how we can fine tuning of the models. So the first thing, it is the classical example. It is the categorical, it is the simulation with categorical variable. So we have for example, the training image here, and 2 possible simulations that we can obtain without any option from only this training image. We can also do this simulation with a continuous variable only. So we have the training image like previously, and we can obtain this type of simulation. We can mix or different type of variable. So in this case, for example, we mixed the categorical information with the continuous variable. And like that, we can obtain for different simulation for the categorical information and for the continuous information. So we have different simulation for each variable. So we work like that with collocated variables in the training image and also in the simulation grid. So we specify in this case for each variable independently or 3 parameters. So the distance type, the pattern geometry, and the size to define the number of neighbors, and also the threshold. The scan of the training image is stopped as soon as all patterns have reached the threshold, for example. And 2 simulation modes are available. So we can work one variable at one location simulated at a time, or all variables at one location simulated at a time. Another example here, it is if we want to use a rotation. So in this case, we work also with the same training image, and we add an information on the rotation. And like that, we can obtain this type of simulation. So we simulate structure with different orientation from the training image. We can apply this rotation globally, so same transformation everywhere, or locally. So in this case, we require map of angle or something different, and it is what we can see in the next example. So here we define a scaling along X and another scaling along Y. And we can obtain with the same training image this type of simulation. And like that, we can see the difference between the top and the bottom. So along that take into account this information. And we have also a difference between the west and the east with that take into account this information. The last, not the last, but an important constraint can be from the proportion. So it's another example here, but we have this type of training image. We use some proportion, and we can obtain this type of simulation. Here we can also work globally or locally. If we work with a global constraint, target probability is for each class. And if we work locally, we support a different proportion for different place. The last example that I want to show you concerning the constraints that we can put, the different options that we have, it is if we want to work with hard data. So in this case, we work always with the training image, so we can have something like that. And we add some conditioning data from wells, for example, and we can also add some other information like a rotation or something like that to obtain this type of simulation. And like that, we have seen all the different options that we can use and all the different simulations that we can obtain with the direct sampling. So now I want to show you how it is implemented in Isatis.neo, and you can see like that it's easy to use it. So I quit the presentation, and normally you can see our software. So the tools for multiple statistics is this one. So at the beginning, you have to define which training image you want to use. So you put the data table with the training image just here. You can add a selection if you want. If you want to use some conditioning data, you can check this information here, and you put the data table corresponding in this part. And after that, you just have to define the different variables that you want to use. So in the first case that I want to show you, I can select a categorical information, but I can also select a continuous one. And after that, I select the corresponding variable in the training image. And like that, after, I have to define the grid for the simulation where I want to put the result. And after that, I have all the different options here. So for the first example, I want to show you without any option. So I can click on next. And now I have to define the three important parameters. And so we have the first one, it is the threshold. After that, we have to define the number of nodes for the neighborhood. And the last one, it is the fraction where I want to compare all the different cells on the training image to obtain the result on the simulation grid. I can calculate a preview of one simulation in order to check if all the different parameters are correct or not. And after that, I click on next, and I have to define the number of realizations that I want to obtain. And I see the name of our output. When everything is defined, I click on finish, and it is really quick, and I obtain directly the result in the display part. So here I have the training image, and now I have directly the result that I can obtain on a simulation and the result on the other one. So here it is the result for my two realization. So now if I want to use an option, I just have to select which one I want to use. And after that, I can define the parameters for this option. So like I said previously, we can use and we can work locally or globally. So in the case of we work locally, we define the value for this scaling. And if we want to work locally, I define the variable with the information that I have locally. So here I have this type of information, and that corresponds to this example. And I can see the same thing for the other axis. And like that, I can see exactly the same information that I have and that I want to use for the simulation. When everything is defined, I click on Next, and I have the tab in order to define the 3 parameters. So I have by default some information, so I can keep it. I click on Next, and I have exactly the same window to define the number of realization that I want to obtain. I click also on Finish, and I obtain 2 simulation with these parameters taking into account. So like that, I have something here directly in my project, and if I want, I can reproduce all this different information or all the different realization, or I can change some parameters. If I come back on the presentation now, like that. I think you see now again the presentation. So now I want to talk about the training image and how to get it. So several options are available. So we can using a drawing software such as GIMP, and it is the case in this training image. So like that, I can display directly the training image that I want to use. We can also work with geological analog, so like here with an outcrop or an RGB image like this one. Or we can also work and build with a simple mathematical formula in Isatis.neo calculator, and we can obtain something like that. And we can also work with Python libraries because it's available in Isatis.neo. And we can also use some other simulation techniques, including process-based. So it's very easy to work with the training image and to define the training image. So now just a few words about geovariance. If you don't know us again. And I have small. Oh, okay. So who we are? We are global provider of geostatistic-based solution. We are the leader and a reference on the market. We have some exclusive technical partnership, like with Neuchâtel and also with the Center of Geostatistics from Paris School of Mines. We are founded in 1986, so we have more than 35 years experience in geostatistics and software development. And we are more than 30 technical experts, and we have different expert consultants and also experts in the software developers. We are based in Fontainebleau in France, but we have also different offices in Montreal, in Rio, or in Belo Horizonte, in Santiago also, and of course in Perth in Australia. So now you have an overview of what we can have and what we can do with the multi-point statistics with Isatis.neo. So to go further, if you want a training on these techniques, we organize one with Philippe and Julien, so in partnership with the University of Neuchâtel in February. And during this training, participants will learn the fundamental aspect underlying the multi-point statistics approach, and will have the opportunity to apply them in practice through a series of tutorials and hands-on with Isatis.neo. We start this training with an overview of geostatistical approaches. We present during this course the concept of training dataset and training image and general principle on direct sampling algorithm. So I don't want to give you all the details, but if you have a look on our website, you have everything with all the details for all the day. During this training course, we explain in detail each parameters and constraints, and you learn how to use them to test different parameters with Isatis.neo on real cases from different domains of application, like hydrogeology, reservoir, and we have also an example on a fluvio-glacial aquifer. So if you are interested in this training, you can register on our website directly, or you can send us an email. To go further, we can also organize some consulting services around only the data analysis and quality control, or around the ground and groundwater modeling. We work also on services around the risk analysis or for routine automatization, and of course for the mining domain in resource estimation and classification. It is also possible to try our software and our technology. So we are here for you proof of concept related to the implementation of our software solution on your data, and we work with you on your data in order to help you to understand what we can give you and how geostatistics can help you. So if you need that, you can ask for your trial. So I have finished with the presentation. So now, if you have any question, you can ask your question in the question part, in the question zone, in the GoToWebinar interface.
So I think we have already a question from Bruno Honorio. Maybe I read it so that everybody hears it. Many thanks for the presentation. Can you elaborate more on the selection of the training image in a general sense? How is the relationship, if any, in terms of size of the TI versus the volume to be simulated? Also thinking about the grid size, do they, TI and simulation, need to be at the same scale? So there are many things about the training image. So the first point, for the selection of the training image, what we recommend now is to do it via a cross-validation exercise. So usually we try different training images, and what you also have to have in mind is that the training image is not exactly what you would get in the end. the training image is one component of a process in which you have also to model all the non-stationarity, which is often very important. Like you have trends, maybe you have orientation that changes, you may have the dimension of channels that will be moving, so that you have plenty of other ingredients. And we put everything into a cross-validation exercise. So you put all these ingredients, you remove a part of the data set, a part of the boreholes, try to simulate at these boreholes, get uncertainty estimates at your borehole, compare with the true values, get a score, and then you change the parameter, the training image, maybe the trends, and etc. And then you can have a good idea of which training image is the most adapted to your problem. And sometimes training images can be very simple. They don't need to show all the details of the problem. So that's something that is often difficult. Often we try to make training images that are too complicated and that they are not the best for the problem that we want to solve. So I hope that answers the first question for the how to select the training image, and then the relation between the size of the training image and the volume to be simulated. What is very important is the size of the training image versus the complexity of the patterns that you try to model, more than the volume of the simulation. So, I mean, if you have simple objects, like in the examples that were shown just before by Hélène, where you have these simple lenses, the training image can be rather small, even if you want to model a big domain. But if you have very complex curvilinear patterns, maybe coming from a process-based simulation in which you have little repetition of the patterns, then you need a bigger training image to have more examples to be able to derive statistics about the spatial patterns. So the size of the training image should be in relation with the complexity of the patterns that you try to model in order that you have enough repetition in the training image. That's the idea. And I think there was a last point. Need to be at the same scale. Do the training image and the simulation need to be at the same scale? It is best, but you can play with these factors that allows to dilate or contract, shrink the pattern. So this is not an obligation. Now, if I did not answer everything, yeah, just let me know.
Another question from Adrian: is the global CDF and variogram reproduced if doing simulation of continuous variables?
Normally, yes, but of course it depends on the complexity of the patterns and the parameters that you put in the simulation. But normally, yes. Yeah.
And from Alejandro, when you scan the training image, you define a fraction of the total number of nodes to try?
Yes. The idea is that the scanning of the training image is done in a clever manner so that we go everywhere in the training image. Julien developed a nice algorithm that ensures that. But we don't want to scan all the nodes of the training image because otherwise we would just copy and paste always the same stuff. So we fix a maximum proportion of the training image that we can scan. And often we get very good simulations with rather small scan fraction, like 10, 20%. And so from one node to the next, the nodes that will be scanned will be different. And this will ensure some randomness in the simulation, and will ensure that we don't copy paste exactly the training image all the time. So it has two advantages. It's faster because we don't scan everything, and it ensures also variability. Yeah.
And the last one from Ayet: does MPS method work fold reservoir?
I would say yes, but we would have to look at the detail and the case. So normally when you work in a folded reservoir, and if the correlation follow the fold, I'm having in mind something like a big anticline, and you may have correlation along the axis of along the sedimentary structure, basically, and this is folded. So we usually start by unfolding the system and putting all the calculations, making all the simulations in the stratigraphic formation, so following the stratigraphic layer, and then you have the correlation that properly follows the folded structure. So this requires some preliminary work usually in advance to be sure that we do the things properly. If of course it makes sense for the sedimentological aspects. I hope it answers the question, Hayat. Any other question?
On the electromagnetic study, can you comment about what was used as training image and what was used as hard data?
Yeah, so that's an interesting case that we call gap filling, because the data are so dense that we use the data themselves as hard data and as training image. So everywhere where we have data, we just leave the data. But in the zones where we have big gaps, we fill the gaps by somehow resampling the data. So the training image is used to fill the gaps without having to add any additional information. Is it clear?
I think so, yes. From Ayat, geological cross-section will be the training image?
Yes, they can be. Yeah, that's correct. There was an example with an outcrop of a geological section. What is difficult when we do that is that often you have some trends, some non-stationarity in the geological section that we have, and so we need to give some information about that non-stationarity. Otherwise, you mix up all the patterns. But this is feasible using the multivariate tools that we have in DeeSse. Yes.
And another question from Christina. What's the advantage when I compare direct sampling code simulation using seismic and MPS?
So I'm not sure to understand precisely the question. Advantage if you compare DeeSse alone, DeeSse with co-simulation, or DeeSse with another MPS technique. Can you be more precise, please? If maybe I just make an assumption. If I compare DeeSse with other MPS techniques that are often available, like SNESIM, the other MPS techniques, they don't offer the possibility to work with continuous variables. So you would have to make categories and work with categories. With DeeSse, you can work directly with the continuous variables. Sometimes you don't need it, but you have this flexibility. And the other flexibility that you have is that you don't need to make regions. So if you have orientations that fluctuates, you can just use the orientation, the angle, the exact angle anywhere where you want. And we can also give tolerances on the angles. So you can say, here I know that I have a paleo channel that is, I have to turn my training image between 10 and 20 degrees. And any angle in between is acceptable. And for every realization, I will let the channel fluctuate in these directions. And this often you cannot do with the other MPS algorithms. But I'm not sure to answer precisely your question, Christina, I'm sorry.
Do
Thanks.
you have some other question? I think it's all. So thanks everybody. If you have more question or if you want more information about these techniques or about Isatis.neo or whatever, you can send us an email, and you will receive also an evaluation form. So you can ask all your questions in this evaluation form. And thank you for everything, and see you soon.
Bye-bye. Thank you.
Bye, thanks.